The electric field is discontinuous. For r greater than, or the magnitude of little r greater than big R, we have this equation above, and this can be separated into three different terms. The first term for r equals 1, this is outside of the sphere, and for the other two terms, the little r, or where the delta function is going to find value or find a charge position, I'm doing air quotes, is at 1/2 r, and then the other is at 0. And so that's drawn on here with the sphere. So we're going to just work through the problem quickly, and it'll be fun.
For part A, we're going to find the charge density inside the sphere. Charge density equals epsilon naught times del dot E. Because we're working inside the sphere, where little r is less than big R, E equals 0. So now we have epsilon naught times del dot 0, which equals 0. For part B, we're going to find the charge density outside the sphere, where little r is greater than big R. Because of this, when looking at the electric field, you can see that only the first term is outside the sphere. Also note that del dot r minus r1 over r minus r1 cubed is going to equal 4 pi delta function cubed r minus r1. Now, when you take epsilon naught times del dot E, you're going to have epsilon naught times q over 4 pi epsilon naught times 4 pi delta function cubed r minus r1. Therefore, the charge density outside the sphere is going to be q delta function cubed r minus r1.
C, we want to find the electric field on the outer edge of the sphere. We want to also show that this is in the r hat direction. We can use symmetry to make this problem easier. We know that this is a sphere, and because we know this, we also know that it has azimuthal symmetry, and so we only have to look at the x and z plane. And so we can put our r vector in terms of x hat and z hat, and then we can change that into spherical symmetry through the r sine theta x hat plus r cosine theta z hat, or actually azimuthal symmetry, sorry. And then we can plug these in to our equation for our electric field.
After a lot of algebra, the electric field outside the sphere should be this, in the r hat direction. For part D, we're going to find the surface charge density using E above minus E below equals sigma over epsilon naught. We already know that E below, or within the sphere, equals 0, and we had previously found E above. Using these two values, we can find sigma, the surface charge density in the r hat direction.
We can sketch and visualize this charge distribution as we see here. The positive charge that's in the 2r position, so r1, that adds some excess charge to the distribution. And so we see that a lot of the electric field lines, which are drawn in green, they go off into infinity. And so some come to the sphere where the top part has a negative charge distribution and the bottom has a positive charge distribution.
For part E, you'll take the integral of sigma dA to find the net charge.